Hi everyone, welcome to week 2. Next week, I'll be shaving my head for charity, so I won't look so wild and woolly. Last week we looked at sequences. I've been gathering some info from everybody about what they've been struggling with. Quadratics and logs seems to be the common one. Been speaking to Kara and QCA and some other maths teachers, and there doesn't seem to be a lot of consistency between the schools with what you guys are actually doing in grade 10. They call it 10A. It's often called 10 methods. 10 methods doesn't actually exist. It's known as 10A maths. But sometimes the schools will start unit 1 of grade 11 at the end of grade 10, or right now actually in semester 2. If you're watching, let me know what your school has done so far and what they're planning on doing. But my plan is to finish the sequences today. We're going to finish with geometric sequences and using geometric sequences to look at investments and loans and calculate the value of an investment over 100 years using our recurrence relation that we used when we created last week. Then we're going to look at everyone's favorites, maybe the final 15 minutes. So we're going to try and keep these to 40 or 45 minutes, maybe even 40 minutes, but I'm going to do it probably an extra 2 recordings to make up for that. I don't know many people that can concentrate on methods for longer than about 40 minutes, maybe 45. See how we're going. So my voice is much better now. So if we look here, this is should be about the end of unit 1 for the grade 11s. Some of the year 10s will be doing this semester, depending on your school. If you're watching this, if you could email me through. For this, I'm going to use the textbook. For SURDS, I'm just going to go rogue with the whiteboard and we'll do it as we go. So what we're looking at here is a way to model investments over an indefinite period of time using our recurrence relation, the same one we used last time when we're modeling decay, when we're modeling a ball bouncing. It doesn't really matter. We can use some form of recurrence relation to calculate it. When we're looking at, does everyone know what interest is on an investment?
Yeah.
So you put money in, the bank will give you 5% per year, calculated depending on monthly, yearly. At the end of that year, you get 5% of your investment. Simple interest, you're just getting that at the end of the year, and at the following year, you get the same amount. If you were to look at compound interest, in the first year, you get so you start with $100. At the end of the year, you add 5% onto that. Now for the second year, we have our starting point is now year 0 plus 5%. So it's not as simple as modeling with simple interest. We need to start playing with a few indexes and things like that to be able to model it over 10 years, 20 years, however long the investment might be. So we can do it, and I'll show you guys the painful way first. So we can do $5,000 invested at 4% per annum, compounded yearly, meaning that $5,000 at the end of each financial year, 4% of that investment will be added on to the end, to the initial investment or the initial capital of $5,000. So we can sit here and we can do this way. Okay, so at the end of the first year, we have 5,200. Okay, at the end of the second year, we have 5,408. Does this look like a very efficient way of calculating interest?
No.
What other way could we use, Henry?
Geometric sequences.
Yes, we can use a geometric sequence or a recurrence relation. So when we're looking at the interest rate, and a lot of people in methods actually forget the absolute basics of maths when they get to grade 11 and 12. How do we demonstrate a percentage as a decimal? We divide it by 100.
Yeah.
4% is 0.04. And the amount of times I've asked grade 12 students that and they couldn't tell me how to calculate a percentage from the decimal from a percentage number. So to calculate the next year, we times it by 1.04 because that gives us in our answer the starting balance and then 4% interest. So we remember the geometric sequence. The first term is A0 or the amount of money that's invested. The common ratio here is 1.04. Why is this not a arithmetic sequence?
Because it's going up by the same amount each time.
Yeah, it's not going up by the same amount each time. There's a consistent ratio, but the number that it's increasing or decreasing by is different. So we can use our recurrence relation. I want everyone to write this one down. We've got, I'm going to use the whiteboard after this for everything else, but there's just so much writing in here that it would take me forever to. So A0 is the principal. AN is the value of the investment, okay, at 10 years, 20 years, 2 years, it doesn't really matter. R is the interest rate plus 1 as a decimal. So in this case, it's 1.04. And then the interest rate is the periodic interest as a decimal. So here we've got, and I might actually use my whiteboard behind. So I want everyone to write down $30,000. And I'll stop sharing so you can actually see the whiteboard properly. So we've got A0 is 30,000. Interest rate is 1.05. And we want to write a recurrence relation that gives us the amount at any given year. So 5% interest. Can you see the whiteboard?
Yeah, I can see it.
Yeah. So the value of A0 is $30,000. The interest as a decimal is 0.05. So we know that our recurrence relation should be A, the number of years plus 1 equals 1 plus our interest rate as a decimal, and then AN. If you were going to sub those numbers in, Henry, what would your final recurrence relation look like?
1.05 AN.
Perfect. Because that would give us the value after 1 year, after 2 years, after 3 years. Again, we would have to do this each year, and I'll show you why this is not very efficient now. So we would have to do that for each year though, wouldn't we? So you could just put it into your calculator and keep pressing equals. I want everyone to have a think for 2 minutes. What equation would you write to try and solve this for any number n or any number of years? So 2 minutes, have a think. What kind of equation could you write that would allow us to solve this? I mean, this is massive extension for grade 10, grade 11, but it allows me to see how everybody's brains work. And then we're going to go back to SURDS, polynomials, and everything, then logs. You guys have said you were struggling. So 2 minutes or 1 minute left. If you're watching the recording, you can skip through, or you can have a think about what kind of equation we could use to solve for the value of the investment at any given year. Did you go that far in depth, Tyler?
Sorry.
Have you guys gone? Oh, not Tyler. Henry. Sorry.
Yeah.
Did you go that in depth with your?
A little bit, but not like
Yeah.
super depth.
Yeah, that's fine.
I know the formula, but
Yeah. So, Henry, how could we calculate the value of the investment at any given point?
A equals P, and then in brackets 1 plus R over M, and then close brackets to the power of MT.
Correct. You can also use this one. I'll give you now. It's probably a little bit simpler. So we've got A equals P 1 plus the interest to the power of n. Is this going to be a linear or an exponential function? So take 30 seconds. Is this going to be linear or exponential?
Exponential.
What?
Exponential.
Yeah, so when we have a linear scale, what happens on a linear scale?
Oh, it's increasing by the same amount each time.
Yeah, we get a nice straight line.
Well, this would be changed because it's not always increasing.
So it might start here and it will slowly increase. And what shape do we get?
Okay.
We get a J curve. So arithmetic sequences are linear. Does anyone need to go over like the real basics of y equals mx plus c, calculating slope, calculating midpoint, calculating unknown x values and unknown y values? Is everybody okay with that? If you're watching the recording and you're not, then I can do a lesson on graphing as well, where we do the more complex 10A graphing. How are you with your graphing, Tyler? I mean, not Tyler. I'm terrible with names, in case you hadn't realized. Henry, how are you with your graphing?
Yeah, I'm pretty good with.
Yeah, that's fine. So the arithmetic sequences and geometric. So the exponential curve comes from a geometric sequence. Arithmetic sequence gives us a linear curve. What's something you've done so far where you were looking at exponential graphs and exponential equations and things like that?
Yeah.
Where you have you done the modeling of flu outbreak yet?
No, I don't think so.
So one of your assignments should be to model the flu outbreak. So a flu outbreak starts with 1, goes to 2, goes to 4, goes to 8, goes to 16, 32, and we get this kind of curve. So it's an arithmetic sequence because it doubles each time. So you start 1, 2, 4, 8, 16, 32.
No, we haven't done that. We've done an assignment like using functions to like outline a mountain range. But
Yeah, so this is slightly different, but you'll use exponential functions to model a flu outbreak using various functions on the calculator. But this week is pretty much an intro. Now that I kind of know where everybody needs to work on, now I can be a bit more specific. So that's the equation that we use up here to calculate our investment at any point in time. I want everyone to practice using that formula. So have a go at using that formula. You'll see how easy it is. Use your calculator. Everybody got Texas Instruments? What calculators have you guys got?
graphics.
Yeah, is it a Texas Instruments or a Casio?
Texas.
Okay, cool. I've had my Texas Instruments calculator since I did methods in 2004. Still going strong. So $15,000 deposited, 6% per annum interest rate. What's the value of the investment after 6 years? It should take you about 2 seconds to put that formula in. And the interest is compounded yearly. Any ideas? It looks something like that.
Yeah.
We've got the initial investment here, $15,000. 1, and then we've got 0.06, because the 1 represents this number, and the 0.06 gives us the percentage, and this is our exponential function to the power of 6. What if I said to you And again, this is just, I want you guys, if you're watching the recordings, to send your answers to me. Even, I'm obviously going to go through the answers, but if you got them wrong, we try and figure out why you got them wrong. What if I said compounded monthly?
You would do 6, the n value would become 6 times 12.
Yeah, or you could do 0.06 divide by 12. And then just sub that into 0.06. That would give you the monthly. And you could change this to, or you could change that to 60. All right. Everybody remember SURDS?
Yeah, but I'm not the best. Actually.
That's something you think you need to work on, because that's what I'm going to do.
Yeah.
All right. Let me bring up my cheat sheet for SURDS. Rational and irrational numbers. Anybody remember what they are?
Not too. No.
So in the middle, we've got natural numbers. So these are numbers like 350, 5, 12. Next circle, we've got integers. So integers are 0, minus 10, minus 24. Feel free to copy this down. It's a good cheat sheet.
What does the middle circle, like the little circle say?
Natural numbers. Next one is integer. Then we've got irrational numbers. Do you remember what irrational numbers are?
I like fractions.
Yeah. Half, 3.25, 7.6. They are not exact. Irrational numbers are not exact numbers, and we don't like using them in methods because of rounding. What's the biggest problem with rounding? Anybody know? We risk making rounding mistakes. So when we are doing very complex maths, when we are doing long-term forecasting and modeling, we do not want to be rounding. When
what does the middle circle say? Does it just say integers?
Yeah. So we do not, when we're doing modeling, we're doing long-term forecasting, we're doing complex maths, we want whole numbers. Or exact numbers is more the technical term. Because if you forget to round, or if you miss round by 0.01, and you're only doing 1 or 2 further calculations, does it really matter? Is it going to make a huge difference?
No, not too much.
And also, obviously, it depends on what you're modeling as well. If we're working on the COVID task force, just make sure you guys can see what I want you to see. So we're working on the COVID task force, and we are making decisions based on mathematical modeling of the COVID outbreak to give advice to the Prime Minister or the Premier of Queensland. That it's probably a little more pertinent to make sure we don't have any rounding mistakes.
Yeah.
So these are irrational numbers. sorry, these are rational numbers, not irrational numbers. Sorry. Rational numbers, not exact. We do not use them in complex maths because we will make rounding mistakes. Our calculators will make rounding mistakes. They will round in the wrong place. Where should we round if we're doing if we're doing complex calculations? Should we round at the end, the middle, or the beginning? So if you are using rational numbers, always round at the end. So everybody got this copied down? Everyone get it?
Yep.
Rational numbers, not exact, not what we want to use when we're doing long-term forecasting, when we need to be very precise. On the other hand, we have irrational numbers. My wife stuck sticky tape to my whiteboard, so I'm still trying to get it off if you're wondering what all that crap on there is. So, what else we got? Square root of 3. How many, okay, here's this. How many numbers could be the square root of 2? What are the two possibilities?
One.
One, or what about -1?
Yes.
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 And rational numbers typically can't be made any smaller. So now we'll introduce the concept of SURDS. So why do we introduce the concept of SURDS? Because we do not want any mistakes. Okay. The area is 3 meters squared. Can you guys calculate the side length? This is meant to be a square, by the way.
1.5. No.
And how can we represent that using an irrational number? So no decimals, no fractions.
Not too sure.
So we could do, so if we were, bear with me, obviously it's not going to be used, but what's the opposite of squared?
Square root.
So each side is going to be the square root of 3. I think it's like 1.73 as a, I think that if you were to do the square root of 3, what do we get? Got your calculator there? I don't have one on me.
Yeah, I'll get one. It is.
So another word for this irrational form is the exact form. I'm pretty sure I've heard Tyler being told off by Kailash for this, with the SURDS and using them rather than the decimals. So 1.73, the square root of 3.
Right. Yeah, 1.73.
Okay. So always, if we're doing complex maths, we use the surd form or the exact form. And why do we do that?
So we don't make any rounding mistakes.
Exactly. So 1.73. I think the actual number is like 11 numbers long. 1.73 and then like 9 more numbers, right?
1.732050808.
And where do we stop the rounding? Yeah. So the idea is we just do the inverse. So instead of it being 3 meters squared, we say each side is equivalent to the square root of 3. That way, we're never going to make any rounding errors. There's 3 rules that you really need to know because we can't simplify the square root of 3 anymore. But sometimes you're given, with surds, you'll be asked to simplify something. So the square root, these are the 3 rules that I think you should live by in methods. We have the square root of AB equals the square root of A times the square root of B. So this is when we're looking at simplifying the surds. Because it would be just as silly to use a decimal as it would be to use an incomplete or non-simplified surd. The second one is the square root of A times by square root of A equals A. You should be able to use these 3 rules to simplify any of the surds. So we've then got square root of A over square root of B equals square root of A over B equals the square root of A divided by B. Now we use these 3 formulas. Apologies for my board. My wife decided to stick a bunch of stuff to it and now it's wrecked. I'm going to buy a new one just to punish it. Spend like $200 on a whiteboard. So I give everyone 30 seconds to write those down. We're not going to go hugely in depth today. Now that I know what you guys want to work on, I thought I'd introduce this topic because it's one that everybody struggles with. I had a few emails come through today. That's good. Quadratics, logs. I think surds as well. We'll maybe do some more hardcore surds next week. All right, so I'm going to rub these off. So we have, I want to simplify the square root of 12 because that isn't simplified as small as it can go.
It can be the,
sorry?
could it be the square root of A times the square root of B? So it'd be the square root of 3 times the square root of 4.
Yeah, either or. I thought you said you struggle with surds. You're doing fine.
No, these ones are fine. It's like the it's like the complex ones.
Yeah, no worries. I always, with my seminars, I always start basic and then build up to the complicated ones.
Yeah, it's like when you're giving like a hard quadratic or something and then it says put the answer in a surd form or something.
Yeah, so actually when you have to calculate the answer, then put it into a surd, is that where you struggle?
Yeah.
Yeah, that's cool. Well, next week we'll do quadratics and usually most of your answers and most of your calculations should be done in surd form anyway.
Yeah.
So what would, using the second formula that we wrote down?
That would be the square root of 50.
Yeah, perfect. Third one, what we've got 50.
Is it 50 divided by the square root of 50?
Oh, no, just right. Realize what I just wrote. So we got 50 So to simplify this, we can now simplify this further. So we've got 50, and now we're going to link the rules together. 50 equals 10 times 5, 25 times 2.
Yeah.
So we could write the square root of 25, getting a little bit convoluted now, times the square root of 2. We can then simplify it to the square root of 5.
5 times
5 the square root, yeah, 5 times the square root of 2. So we can further simplify that down as well. So what about if we have, keep it fairly simple and light today. We'll ramp it up to week 3 once everyone's had a chance to catch up and watch. So square root of 12 over square root of 6.
It would be, that would equal the square root of 2.
Perfect. So I'll just step it out for everyone so that they get it. So we would then have this as square root of 12 over 6 because we don't need the square root over both numbers. We can then do, if we do square root of 12 divided by 6, we can then further simplify it to the square root of 2. Now, using SURDS when you've not simplified things is probably just as bad as using decimals. My wife just sat down, she studied maths as well. She just said, ugh, SURDS. So you guys are not alone in your hatred of SURDS. All right, let's finish off with some questions based on these 3 simple laws. And we'll get more complicated next week and we'll start mixing it with quadratics and logs. And we'll probably practice questions where we use decimals and incomplete numbers of 1.75 rather than one of our SURDS. And we can actually see the difference in the answer. So if you were to simplify the square root of 8, what would you guys do?
Square root of 8. 8 squared. You can do the square root of 4
Yep.
times the square root of 2. Then that would become 2. The 2, where you put the 2 outside the square.
Yeah.
2
times the power of 2. So if we did another one, you guys are flying through these. I think like what happens with a lot of method students is that your teacher's quite good at explaining the concept, but then when you've got to mix those two concepts together, like mixing a surd and quadratics, you're not really quite sure how to implement it. Is that
Yeah.
a valid thing? Okay, cool, that's good. You don't seem to have a problem with the surds themselves.
So that would equal the square root of 8 times the square root of 4.
Yeah, so what would that give us?
2 square root 8.
So we'd have the square root of 32 because we need to simplify here.
Yeah.
We can then simplify 32 even further by making it
8 and square root of 4.
yeah,
And
16 and 2 is what I would have done. I don't think it really does.
So 4 and 2.
Yeah. And then you've got the 4 times by the square root of 2. And that's simplified all the way. It doesn't really, you should get the same answer here with 4 and 2 at the end, depending on how you simplify it. So square root of 9 times 9. Just realized I wrote my answer before I wrote the question.
I could do you do the square root of 2 times the square root of 9, so you'd get 3 times the square root of 2.
Perfect. All right, last one. You guys have flown through that. We'll get more hardcore next week. I think some more painful questions for you. We'll start doing quadratics. So decide if we're going to do quadratics or logs first. Depends how much pain I want to put myself through next Wednesday. So square root of 18 over square root of 9. And we'll leave it there.
Is the square root of 2.
Okay, so we just change it to, we just rearrange it. So square root of 2. Can you simplify any lower than the square root of 2?
No.
No. So if you find the answer is the square root of 2, great. All right, guys. That's the end of like the introductory stuff, seeing where you guys are at. You guys have sent some emails, so we're going to hit quadratics and logs, and there's a few things in the 10A curriculum that I'm wondering if you guys need any assistance with. So exponential equations, might do some of that as well. So we'll probably start in the 10A logarithms and then work up to the unit 1, grade 11. That way the year 10s are getting what they need, the grade 11s are getting some great revision, then the year 10s can be extended and the year 11s can get some revision as well. Because with methods, if you miss one part in grade 10 or 11, it's really difficult to catch up. And you might end up just being behind by virtue that you're missing a little piece of information. But I think you guys will be fine. I will see you next week.
Okay.